Yes. Okay, my name is Göran Lindström, and I will give you an introduction, a general overview to the HYFO model. HYFO, and some of it will be covered many times, but that's sometimes quite good, so you remember it. HYFO stands for Hydrological Predictions for the Environment. We debated quite a bit about whether this was a good name or not, but it's easy to remember, and I think that it's worked well. HYFO is a Fortran 95 model code that Lotta is maintaining and writing. And then we have different HYFO models, setups, SHYFO for Sweden, EHYFO for Europe, and so on. We call those model setups, or HYFO models. So the code and the model. Components of HYFO. Well, it's like most models, divided into subbasins, different land uses. So we have the different land soil classes, layered soil, and a network of rivers and lakes. You can also use regional groundwater flow between subbasins, and there are many different ways of managing water, like regulation, point sources, wetlands irrigation, and so on. To begin with, the model was developed for simulation of nutrients, so there's quite a lot about nitrogen and phosphorus, for instance, atmospheric deposition of phosphorus, and so on. Okay, we started with a sort of a pre-study in 2004, and then we started the main development in 2005. So I was quite happy. Now we had the chance to work really thoroughly with one experimental catchment that we have near Norrköping, Stubbetorp. And when we fix everything there, then it's just a matter of scaling up to the rest of Sweden. I had no idea that we would even work outside of Sweden at that time. But after a while, Beard came and said, remember that you have to be able to run the whole Baltic Sea drainage basin. And I was quite overwhelmed by that, but okay, let's see, how do we do this? And now we're talking about the whole world, so it's an upscaling. We didn't want to get stuck in this small experimental catchment, and even if we had worked there for 3 years, we would still have many unsolved questions. So we started the other way around. We started with the large scale, and then gradually increasing the detail. And Beard touched upon this. Why a new model? There were already so many models. At the SMHI, we have also the HPV model that you may have heard of. And the SWOT model is, of course, another candidate for this type of applications. But by building our own model, we could adapt it to our own conditions and the needs that we had, the data that we had available, and so on. We could write a code that we could understand and develop further. And I think that these are very important issues for us. We were able to spend a lot of time on modeling water flow paths because they are important for water quality simulations. But I think the second point is really important, that we have a code that we can actually develop and understand. It's not always so easy if you take another code. So the philosophy was to start as simple as possible and fill in the details gradually. Make sure that we have everything like a skeleton, all of Sweden, and then zoom in. Fill in the details, and at the end it should be good enough. So we get all the essentials from the beginning, and it was important for us also to start doing something which is simple and useful right away, not waiting for 3 years and realizing that it wasn't really what was expected. To describe all processes as simple as possible, but not simpler than that. And we wanted to avoid making some parts too complex. We wanted to have a balance in complexity between different parts of the model. So that, for instance, not the river part would be dominating when it comes to computational time and so on. And the reason for filling in the details as you go along is that you don't want to end up with something like this, where you spend all of your time with the less important parts of the painting, and at the end you run out of time and you have to put something in very quickly. So that's It's quite common. Also, as I said, we wanted to have something useful to start with, and this is an overview of the evolution of the Swedish setup. You will not work with the Swedish setup, but I am personally almost only working with the Swedish setup, so that's what I show here. This is the NSE, or sometimes earlier we used to call it the R2, the Nash-Sutcliffe efficiency. Different model versions, the mean value and the median value, and this is 398 stations in Sweden. Each version should be better than the previous one. Many of these basins are regulated, so that's something which draws down the average. But anyway, we strive for improving the model gradually. So which version is the best? It should always be the next one. Okay. It's a conceptually based rainfall runoff model, and it has nitrogen and phosphorus processes. It's mainly driven by rainfall and temperature data, usually at a daily time step. There is also options to use a shorter time step, and in Sweden we use a 1 hour time step also. You can also use minimum and maximum daily temperatures, and we will come back to that later. It's to estimate radiation, which you can use, for instance, for evaporation. The nitrogen is driven by atmospheric deposition and many other things as well. Okay. It's a scalable application, but it's targeted towards large model domains. I don't know if you mentioned how many subbasins are in the worldwide HYFO. Okay, you will figure it out during the course of the day, I think.
130,000.
Yeah. Okay. The model is divided into sub-catchments, so it's not grid-based. You could, in theory, set it up in a grid-based application if you want to. So these are the different subbasins shown here in the figure, 1, 2, and 3. You usually put the outlet of a subbasin where there is a large lake. So subbasin 1 to 3. And then there is a division within each subbasin into different land and soil type combinations. And each of these have 3 layers. You can have different vegetation types on the different land use classes. Here is an example with different soil depths. It's quite a lot of work in the Swedish application has been put on describing the regulations, but I don't think we will go through that very much. You can also model crop dynamics and have point sources, for instance, wastewater treatment plants and uptake of water for different purposes, pumping, etc. This is an illustration of the basin divide in Sweden in the earlier SHYFO version, which had about 18 or 17,000 subbasins. The version that we have now has 36,000 subbasins, so it's even finer in detail for Sweden. So you can see the basin divides and the network of streams. So each catchment consists of different soil and land use combinations. We call these SLC, soil and land use class, or soil and land use combinations. SLC is a key word in this model. Sometimes they are referred to as hydrological response units. So you can use either word, SLC or hydrological response unit, or HRU. What you do is you overlay information from soil data, land use, and create, and sometimes crops if you work with water quality. You combine them into soil land use classes, and you group the individual parts of each soil land use class within a subbasin into one lumped area. So you do not distinguish between parts within a subbasin that are located at different places. It's lumped in that respect. Most parameters in the model are linked to either soil type or land use. You can think of hydraulic parameters such as field capacity or transmissivity, conductivity of the soil. That is related to soil type. It depends on the type of soil, whereas, for instance, evaporation, snow melt, and other factors are usually related to the land use types. Okay. As I said, the soil is divided into 3 different layers, and this is fixed. You cannot choose to have more than 3 layers. You can, however, have fewer than 3 layers. But personally, I think that it's usually wise to have the 3 soil layers. Very thin soils might be described by only 1 layer. These have different thicknesses. You specify the thickness of each layer. We have had a tendency to divide these into quarters of meters, so each layer would be a multiple of 25 centimeters. That is the tilling depth, basically, when it comes to agriculture, the depth that you can modify by tilling. So 25 centimeters, maybe the next level would be 75, and maybe the 3rd layer would be 1 meter, a typical setup. Within these layers, you calculate the amount of water and nutrients, nitrogen and phosphorus, or other substances. Now, what we calculate is the soil water amount in each layer. We will get back to this tomorrow. And then the groundwater level is calculated as a function of the soil moisture. So when all the soil pores are full, that's considered to be groundwater. So groundwater is not a variable of its own. It's calculated as a function of soil moisture. You can specify a certain stream depth to which drainage of the groundwater occurs. There is a tile drain depth, so you can have tile drainage within agricultural soils. And then you can connect regional groundwater between the different subbasins. Now, this type of model exists within each SLC. So in a typical application, a typical subbasin, maybe there would be 10 different SLCs. Then you have the network of rivers and lakes. And blue here means water, green means substances. To start with, that was only nitrogen and phosphorus, but there are other substances available right now also. And then for the lakes, you have to have atmospheric deposition, for instance, takes place here. Okay, more about that tomorrow. We distinguish between local streams that are within each of the subbasins and the main streams that connect the subbasins. We could also distinguish between local lakes and lakes that are located at the outlet of a subbasin. We usually refer to these as I lakes, internal lakes, and O lakes, outlet lakes. And you will get familiar with those terms during these days. So I usually try to get a bit philosophical when it comes to these things. Which model should you use? And I'd make the analogy to photography or something else which is on my mind that particular day. So there's always, as long as I remember at least, maybe more earlier, there was always a very intense discussion about which model is the right one. And it's the same within photography, for instance. Okay, which brand is the best? Is it Nikon or is it Canon or is it something else? So it usually comes down to this type of argument. My model is right and yours is wrong. And there's a very nice quote that we like here. All models are wrong, but some are useful. So all models are simplifications, but they can be useful. And I want to illustrate that with these two different cameras, or basically lenses in that case. This one is very easy to carry with you. It takes nice pictures. It has face detection. The photos are sharp. This one is definitely more correct in certain senses. It's very much more powerful, very high quality. A zoom with a fixed 2.8. It's a very, very impressive. In this ad that I found, it costed $26,000 and weighs 16 kilos. So this one is, of course, the right one. But can you afford it? Can you carry it with you? So sometimes, and if there is a best model, are you sure that you really need it? Maybe you need a supercomputer to be able to run it. So it's always, in my opinion at least, a balance between what you pay and what you get, or the performance and price. Bang for the buck. We want to have something that is useful, doesn't have to be the best model necessarily. So HYFO has many parameters, but it's still possible and fun to tune it. I don't know how many keys there are on this piano, but there are definitely many more parameters in the HYFO model than this. A few years ago, I asked the question about traditionally we've discussed this. How do we avoid building a monster instead of a model? And this was a few years ago, and the answer was already then. It's too late. It's already a monster. But the consensus was that it was a friendly monster. So I found the HYFO monster on the web. So it's really huge, and I don't know how Lotta is able to put in any more features in the model, but every time we come with some new additions, she puts them in. And it still works. And the interesting thing is that with every new version, it even runs faster than the old one. So some examples of what we can model with a HYFO model. And these are selected examples of very good performance. So they are the best within each substance, more or less. And these are all from Sweden. I think you shouldn't expect this type of agreement right away from your model applications in the worldwide HYFO. But anyway, it's to illustrate what type of models the type of variables that you can get out. Discharge, of course, that's the core of the model. We wouldn't have a model without discharge. And these are the NSEs here as examples, 0.94. Water levels, lake water level, this is an NSE of 0.97. Groundwater depth. Water temperature, this is one of the newer features, and this is the record high NSE of 0.99. Now that's it's much easier to get a high NSE with something like that has a very strong seasonal variation that repeats itself every year. So you have to take these things into consideration when you compare the different fitnesses and so on. Okay, and more difficult, nitrogen, 0.6, and a good example of phosphorus here, NSE of 0.5. So it's a variation within how well you can describe the different variables. But it gives you an idea of what type of variables that you can calculate. But I think in this course we will only talk about discharge, but to get the discharge we will also, of course, calculate groundwater, which is always calculated within the model because it's a result from the soil moisture, and lake water levels, because lake water dynamics are important to calculate the discharge, of course. Temperature and nutrients will not be included. Some of the new features in the model, the floodplain model, which is something that we will hear more about later. And we have developed the possibility to model a general substance. That can be either tracers that are conservative or have some other properties. Exponential decay, for instance, if it were a radioactive tracer, such as tritium. Or pathogens, bacteria, could be useful in some of your applications in the future. Sediment transport, which is the latest addition to the model. I don't know if it's in the code already. Yeah, so it's available within the code that you're using. And that's the latest addition. We use the model here for flood forecasting in a tool which is called HYFO Hydrological Forecasting tool. And we have used the HBV model for many years here. It was, as Beard said, developed in the 70s. And this is a more lumped model. So each subbasin here where we have real-time transfer of data is basically lumped or divided into a few different subbasins, and they don't cover the whole area. So the HYPE model has the advantage of covering all of Sweden in very high spatial detail. And the performance of the two models is fairly similar where you have measurements, but then we have the additional, there are some other advantages of the HYPE model. So it's, right, as it is now, it is the tool that we use most for the flood forecasting service. But both of these models are available in HYFO. This is an example of a forecast a few years ago where we had flooding, especially in this area, actually in Norway mainly. And you can follow the flood level as a return period. So yellow here means more than 10-year return period, which is the flood warning level 2 in our case. So you can see quite nicely on the map which areas that are affected. And it's also interesting because you get much more scattered signals. It's like a mosaic of areas where you have a high level, and within that you have a lower level. And that caused a lot of confusion for us because we were used to having large areas which we could treat as sort of homogeneous. But reality is like this. It also depends very much on the lakes. If you have a lake, that acts as a moderator and slows the flow down. So it's basically an illustration of the lake percentage. And we have a lot of lakes in Sweden. Anyway, so it's used a lot. I will talk very quickly about the file structure. It's a bit special because we use text files. And I've been very much in favor of sticking to the possibility to having text files because they are easy to manipulate and import in other systems, for instance Excel or other software. So these are all text files, and the information about each different character is specified within an individual file. So the number of files is not it's independent of the model setup. If you model Sweden or only a small river in Sweden or the whole world, you basically have the same number of files. But the files contain much more information if you work with the whole world than if you work with a small stream in Sweden. But you have parameters. You need parameters if you work for Sweden or if you work with the whole world. You have to have forcing data, observed precipitation, all of it's within one file here. You need temperature, observed temperature, also everything within one file. You don't need, but I'll come back to that later. You don't need, but it's quite useful to have observed discharge. Other variables, that's basically every other variable than discharge. Observations of any type of other variable than discharge is in the xobs file, where x stands for, let's say, unknown or general variable. This can be, for instance, water levels, snow depth, nutrients, etc. You need an info file which instructs the model so that it knows what to do, what type of calculation you want to do. You need the geographical data, It tells you the size of each subbasin, how the subbasins are connected, how the subbasins are divided into the different soil and land use classes, etc. And you have to have a definition of these different soil land use classes. For instance, the depth of each layer, the number of layers, and so on. You may have a lake data file where you can specify the depth of lakes and the regulations, or if you have rating curves, and some other things that you can specify here. When you run the model, this is an old setup, you get a log file in which you can read about the model run. Let's say that the model run doesn't work, then you read the content of this file. Okay, once again, let's start with the hype.exe file then. That is the source code, the Fortran code that has been compiled into an executable file. And you definitely need this one to run the model. The geoclass, as I said, the definition of the different soil and land use classes. The geodata file, fractions, the connection between the subbasins, and more. In the info file, you can also tell the model what output it should produce, what variables you want to print out, for which subbasins, which fitness criteria you want to print, and so on. And I think I covered these. Then there is a small file here, which for some, I'm not really quite sure why we need it all the time, but it tells the model where to find the info text file. I just put it in there, and then I don't look at it anymore. I think most of us do that. If you work with water quality, you have to specify information on crops, how fertilizers are applied, and so on. If you work with irrigation or water abstraction or more complicated types, then you specify this in the management data text file. And then there are many more files that are possible to use, You can see here that it's divided into two different colors: the necessary files or the required files, and then optional files. You don't need observed discharge to run the model. You don't need other observations. And if you don't have a lake, you don't need lakes. If you don't use water quality, you don't need the crop data file, etc. Okay, you went through this, the hype web, the hype code, the wiki, the publications, and the hype tools. The hype tools you will see more about this afternoon. So I'll continue with the Vatten web, which is describes the Swedish application. Let's see if I can open this link. Yeah. This is, okay, it changes the layout according to the screen. This is an operational use of the model where we can see the hydrological situation today compared to what is normal for this day of the year. We've had quite a dry period in Sweden during last year and this year, but it's back to fairly normal values when it comes to runoff in most of the southern part here. It's a bit dry in these areas and up here, but this does not reflect the low levels in the lakes, however, so it's a bit difficult to interpret. Anyway, it's one of the applications. Here is this where you can find information from the Swedish model, and let's look at the Dalälven, which is sort of the heart of Sweden in a way. So if you click on one of these points, you will get the connection here within the river. the hydrological network. And you can see the, it's easier to see in this scale. You can see the basin divides here. It's a bit difficult to see on this screen, perhaps. And then you can download information from each of these subbasins, and you can download information, model simulations for all of Sweden here. There is the application with groundwater that we do together with the geological survey. Here is the similar map to the what I showed you earlier about stream water, but this is for groundwater. The difference between the groundwater situation now and what is normal for this type of the year. And here you can see more clearly that there's a region here with rather low groundwater levels. And you can even compare with the measurements that they have. And I got a hint from Niklas the other day that this one looked fairly well, so we'll take a look at this one. This is the storage of groundwater from the lowest level ever to the highest. So it's a range. And the model is the black one in this case, and the observed values are the red ones. And so you can get forecasts for all of Sweden for the groundwater levels here. So it's an application of the Swedish, of the SHYFO. There are many other things, but something which, we'll look at this. You can see the model agreement with observations for both discharge, low flow, high flow, nitrogen and phosphorus. And you can filter here between large, medium-sized and small basins. Large here means larger than 2,000 square kilometers, and small is less than 200 square kilometers. And I must say, one of the main challenges with the SHYFO model is something that I don't think you will encounter in your work, and it's the very small scale. And that gives new challenges when it comes to the routing of water between subbasins and so on. So there are other challenges in this high-resolution model. We can look at Dalälven once again. And if you click one of these here, you can get a detailed evaluation of the model, a plot here, to see how the model performs when it comes to discharge as a time series. And actually at this point there were both discharge measurements and nutrient measurements. So here is the nitrogen and the phosphorus agreement with observations. Dalälven works rather well, by the way, if you take into consideration that it's regulated. There is also here something which is called the HYFO Runoff Explorer. And I want to show you this one. It is a tool to visualize how the model works. And you can, let's see if I'm able to make it to visualize this. It doesn't fit on the screen. Why is this? Hmm? F11.
Or just F11. Still doesn't fit.
Okay, let's see. So here you have the possibility to look at pre-run model results. You have the temperature and precipitation, evaporation, and the modeled evaporation, modeled runoff. And below here, if you do it on your own computers, you will see it in a better, you will fit the whole picture in one screen. The modeled runoff, snow depth, and groundwater table. So this is the snow here, and this is the groundwater depth, right? The nice thing then is that you can look at this dynamically. I would like to show the runoff for each soil layer, and then you see that the different soil layers show up here. Okay, so here you have the different soil layers. Typically 25 centimeters, I would say 75 and another meter, so you model all the way down to 2 meters. That would be the typical case. And then if you press here, you will see how the groundwater level, when there's precipitation, will increase, and you have drainage through these different soil layers. The drainage from each soil layer is computed individually. And then you have the drainage pipe flow here, and sometimes at occasions there is a red arrow here for surface runoff. So this is you can test this later, and it's a good way of understanding how the model operates. So now you have a buildup of snow here because it's cold. And I'll skip it. And then you can see also the different flow components, the flow from each of the soil layers. And then the water balance up here. The amount of precipitation, the amount of evaporation, and the storage of water within the different, no, the runoff, and then the storage below. Okay, then you can also, if I stop this again, you can see how the model behaves for different soil types. This was a description of how we model a clay soil. If we look at moraine, till soil, it should probably be called till, which is the dominant soil type in Sweden anyway. And we remove the drainage pipes. It doesn't want to. I'm not able to remove that right now, but you can try this later to see the influence of soil type. Okay, so the water balance will be different for different soils. The precipitation is of course the same, but the partitioning within the between evaporation and flow will depend on what soil type you use. If you have a coarse soil, that's usually modeled, in our cases at least, as a much thicker soil. This is sandy soils and so on. You have a larger depth to the groundwater level. Okay, so I recommend that you spend some time playing around with this tool. And now I don't know how to get back. F11 again. F11 again. Thank you. Let's see how this works here. Regulations. I think that, Sweden is a very highly regulated country in many senses, but when it comes to hydropower in particular, this was what I intended to say. And we depend quite a lot on hydropower when it comes to electricity. Almost half of the electricity that we consume is produced from hydropower. So there's a large network of dams. And this shows you all of the major dams as a large circle and smaller dams as a smaller circle. And we can go back to the same river, Dalälven again, and we can see if we can look at the discharge here. So this is a tool for exploring the regulations. And this is the modeled flow under current conditions. And this is reconstructed as how, well, to describe how the flow would have been if the regulation was not there. So to describe the present situation, we need to include all the regulations. But then we can remove the regulations and reconstruct the natural flow. And that is something that we've done quite a lot. It's predefined here for the seasonal distribution. It's perhaps easier to understand if you look at the time series. So you have a very scattered regulation flow. The regulated flow, the real flow is the red one, and the modeled is the gray flow here. Here were some major flood events in the year 2000, two major flood events basically, where there's not very much they can do when it comes to regulation because all the dams are full at this situation. So it's actually easier to model the discharge in a regulated system when you have a high flow, because everything is full. There's not much they can do anymore. So yeah. Okay, I think that's what I had intended to show you now as an introduction.